Our text tells us that friction is exerted by a surface. That, unlike normal force, friction is always parallel to whichever surface is being opposed. Why? Because the atoms of those two different surfaces are colliding with each other. The rougher the surface, the more friction. Things don't stop there, however. There are different types of friction as well: static friction and kinetic friction. Static friction is the force that keeps a still object from moving around on a surface. Static friction points away from whichever direction an object would move in the company of other, usually parallel forces. Kinetic friction is the force that constantly opposes motion. For conceptual reasons, kinetic friction is more simply theorized. There's one more concept to consider when tackling friction, though: the friction coefficient. This concept comes into play when considering the different types of materials that are to come into contact with one another. For instance, a steel ball on a steel ramp might have a friction coefficient of 0.02002, while rubber on pavement might have a friction coefficient of 1.0. This is what got us thinking about ideas for our project, in which I drove my 2000 Toyota 4Runner at a constant speed of approximately 15 miles per hour and, within the frame of a motionless video camera, came to a stop. From there, we plugged the video into Video Analysis, grabbed some data, and set out to demonstrate how friction forces, namely static friction, work. Video Analysis provided us with some awesome data. After plotting some vectors and setting our origin, it was easy as ever to nab our information via graphs. Given were the time and velocity. From there, by Zoom call, Mario and I were able to work out the deceleration of the 4Runner 2. In our case, we were to divide by negative 6.53 meters per second by 2.5 seconds, giving us a deceleration of negative 2.612 meters per second squared. It is important to note a couple of things at this point. A. The 4Runner was capable of coming to a stop in 2.5 seconds. B. The 4Runner has anti-lock brakes, and the wheels never began to skid. This means that the friction calculated, or rather, the friction we are to calculate, was static. Continuing, the two of us decided to calculate the amount of force necessary to stop the 4Runner using the formula for force net, which sets the the net sum of forces equal to the multiplication of mass and acceleration. We have the acceleration, but how about the mass? Well, in this case, it was so simple as Googling the weight of the vehicle and converting to a manageable unit. Why? Because the 4Runner was driven along a path with no incline, and because mass is equal to weight in that environment. In another scenario, the relation between mass and weight may not have been the same. At any rate, Mario and I made the necessary calculations. By replacing the variables in our equation with actual numbers, we received a value of negative 4,709.51 newtons, the force necessary to have stopped the 4Runner while it was traveling at a constant rate of 6.53 meters per second. The last thing required of Mario and I was to calculate the friction coefficient. We wanted to know the ratio between the magnitude of the normal force affecting the 4Runner and the asphalt. To do this, we had to play around a bit to derive a working formula. After setting up a free body diagram, we were able to come to a conclusion that negative mu static times mass times gravity was equal to mass times acceleration. After deriving a simpler formula and substituting our variables, we came up with a friction coefficient of 0.266. This number has no dimensions, as both static and kinetic frictions have different proportions. So that's that, sort of. We might mention that because the vehicle wasn't sliding, there isn't really one singular friction coefficient, as would have been computed for an object with kinetic friction. Rather, this coefficient was the average. Depending on the road conditions, tire compound, and temperature, this coefficient could and would vary.